Today we're going to be talking about numerical integration. Numerical integration is a term for a family of algorithms that are used to calculate the numerical value of a definite integral. It's also referred to as numerical quadrature for historical reasons. In other words, the basic problem is to compute an approximate solution to this integral, the integral from a to b of f of x dx, to some level of accuracy. Generally, we assume that f of x is a smooth function over x, and if that's true, this is relatively straightforward to do. So why would we use numerical integration? After all, if we have f of x, isn't it pretty straightforward to get the integral of it? It turns out that the answer a lot of the time is no, not at all. One possible reason is that f of x is only known at some points, and this could be due to sampling from an experiment or something like that. It could also be that the formula for f of x is known to you, but the integral is hard or impossible to calculate analytically. And this is something that comes across, that happens quite a bit. And then a third reason is that a lot of the time it's possible to find the antiderivative analytically, in other words, to compute the integral analytically, but it's just easier to compute the numerical approximation of it. Now I'm going to show you how to calculate the two simplest methods for numerical integration, the rectangle rule and the trapezoidal rule. There are much more complex ones. In fact, SciPy has a whole integration library called scipy.integrate that has a bunch of different integration routines. However, these two are straightforward to understand, so we're going to do them here. So let's start with the rectangle rule. We have a function f of x, which is shown by the blue line, which we wish to integrate over the interval from a to b, which is shown on this diagram here. So the way the rectangle rule works is that we divide our entire domain up into a bunch of little regions. And each one of them has some width delta x, like that. And then, over one of these intervals, we estimate the area of f of x, or the area under the curve, I should say, as f of a times delta x. And then we do this for the second interval and approximate the area under that interval as f of a plus delta x times delta x. And we do this over and over again for each one of these intervals with width delta x until we reach the point B on the x-axis. And at that point, we now have an estimate for the integral under f of x over the interval a to b. In other words, if I were to say this mathematically, the integral from a to b of f of x dx is approximately equal to the sum of f of x sub I delta x from I equals 1 to n. And in this case, x sub I is a plus delta x, a plus 2 delta x, and so on and so forth. And delta x itself is b minus a over n. So in other words, it's the width of the interval evenly divided by the number of samples that you're going to take. But as you can see, this isn't a great approximation to the shape of the curve. The regions highlighted in red don't get taken into account when we do the integral. And this can balance out over time because some of the rectangles are larger than the corresponding piece of your function f of x, and some are smaller, but not really. So what we want to do is come up with a better approximation to this function, and that's what drives us to try something slightly more complex, like the trapezoidal rule. All right, so how does the trapezoidal rule work? Let's imagine we have exactly the same function f of x and the same intervals delta x that we wish to integrate over. Now, instead of approximating the area under the curve as a rectangle, we approximate it as a trapezoid, like so. And in this case, we calculate the area under the trapezoid differently, or I should say differently than the area of a rectangle. In this case, the area under the trapezoid is going to be f of a plus delta x divided by 2, and then all of that times delta x. And that gives me the area underneath this particular trapezoid underneath this section of the curve. And now I've gone ahead and drawn the rest of the trapezoids in. And as you can see, this does a much better job of following the shape of the curve than the rectangle rule that I did before. And so if I want to write this down as a formula, what I see is that the integral from a to b of f of x dx is approximately equal to, when we're using the trapezoidal rule, the sum of I equals 1 to n from f of x sub I plus f of x sub I plus delta x over 2 times delta x. And so that gives us the area of a trapezoid summed up over all of the small little segments. And in this case, just as in the last one, x sub I is a plus delta x, a plus 2 delta x, and so on, where delta x is the width of our interval, b minus a, divided by the number of intervals we want, n. So what have we learned from this video? First off, we've learned that numerical integration is the term for algorithms that are used to calculate the numerical value of a definite integral. And they do so by approximating that value at several points over some interval that we wish to calculate it over. And there are several possible reasons that you may want to use numerical integration. The function you're interested in integrating, f of x, may only be known at some points due to some sort of sampling issue. A formula for f of x might be known, but it might be very hard to calculate its integral analytically. Or it could be that you can do it analytically, but it's just simply easier to compute the numerical approximation. And finally, we've learned that the rectangle rule and the trapezoidal rule are two fundamental methods for doing numerical integration. And I also showed you how to do both of those methods. And that's all for this video. Thank you very much.